Welcome all. So last time we saw the introduction of the buckling phenomena. We saw the application of different type of buckling loads. We saw the treatment of the pulse buckling, how the pulse buckling is propagating into the bar. We saw the vibration bucklings. We saw the effect of the long duration buckling where the load is lower than that caused by a static case. After that, we saw some complex buckling phenomena also, where the collapse of the wall is to be prevented, and we also saw the interactive buckling between the combinations of the various buckling phenomena. Okay. So, we will continue the chapter and move ahead. So, rings and long cylindrical shells under symmetric loading avoid complexities like in plane stress wave propagation seen in the bar under impact. Okay. So, if we have a ring or a long cylindrical shell structures, okay, so they are not susceptible to the complexities that are occurring under bars under impact. Okay. So, there the treatment becomes easier, okay, and these are stable, more stable type of structures. Okay. Plastic flow buckling of rings is the simplest case. Okay. The formation of the plastic flow in the rings is the most simplest case, okay, and this can be treated with the constant yield hoop stress due to small strain hardening moduli in the metals. Okay. So, these cases can be easily dealt with. Okay. The ring also serves as a fundamental element to study buckle avoidance, okay, during dynamic plastic closure to a solid mass. Okay. So, the pipe closure problem can be dealt with when we are dealing with the ring. The cylindrical shell exhibit a two-dimensional buckle pattern. Okay, as we have seen earlier, there is a two-dimensional buckle pattern. Okay, the buckling pattern is in the radial direction, and the buckling pattern is in the axial direction also. Okay, and imperfection sensitive nonlinear static and dynamic buckling under essentially finite duration constant loads. Okay, so the cylindrical shell will exhibit the two-dimensional buckling patterns, and this will be due to the these are sensitive to the imperfections, okay, that we can see during the static load. Okay. So, due to the imperfections there will be the longer wavelength, okay, in the shells, okay, and they are also influenced by the nonlinear static loading and the dynamic buckling, okay, under infinite duration and the constant loads. Okay. So, now we are looking into the buckling of the simple bar. Okay. So, we are considering the elastic buckling, okay, elastic buckling of a simply supported uniform bar, okay, under axial compression. Okay. So, we have a bar, okay, so we have a bar, okay, the bar is simply supported. Okay. Simply supported means one end is hinged, one end is on free to move. Okay. And we are looking into the elastic buckling. Okay. Bar is simply supported, okay, it is uniform bar. It means that the cross section is same and the material is same, okay, and we are looking this phenomena under axial compression. Okay. So, we are applying the load P as an axially compressive load. Okay. The case is simply supported, uniform cross section and same material. Okay. The bar has length L, the total length of the bar, okay, is L, and it supports an axial compressive force P. Okay. So, the load is applied at P here and there is a reaction P out here at this end. Okay. The bar's cross section is uniform along axial distance. Okay. It means that wherever we cut the bar, okay, we will have the same uniform cross section. Okay. The lateral deflection W xt is taken positive downward. Okay. So, the deflection is taken positive downwards. Okay. So, here positive downwards, the deflection is taken as positive, okay, and it is measured from the unstressed initial deflection W naught. Okay. So, this thing is measurement of W is from the unstressed initial deflection. Okay. So, there will be an initial deflection W naught, okay, in the bar, okay, and the deflection we are measuring from this initial unstressed condition. Okay. So, after that what we do is that we cut a section. Okay. So, between two cross sections, okay, we cut a piece of the bar. Okay. We have cut out a piece of the bar. Okay. Okay. So, this is the elemental section that has been cut. Okay. So, the shear force and bending moments act on the side of the element taken positive as indicated. Okay. So, this is the nomenclature of our shear force and bending moment. Okay. So, as we are moving from one end to the another, okay, this is the bending moment, okay, and this is our direction of the shear force. Okay. This quantity is depicting the inertial effect, okay, and P is denoting the effect of the axial force. Okay. The inertial force acting on the element is denoted by this term, okay, as stated above, okay, where rho is the density of the bar material, A is the cross sectional area, and T is the given time. Okay. So, this is the description of the forces acting on this differential element. Okay. Okay. So, the governing equations derived from dynamic equilibrium of the elemental forces and the moment curvature relationship of the bar. Okay. So, using the dynamic equilibrium, okay, and the moment curvature relationship, okay, the equations fans like this. Okay. So, what we are first doing is that we are summing up the forces in the transverse direction. Okay. So, what we are doing is that we are summing up the forces in the vertical direction. Okay. So, in the vertical direction we have downward force q plus dq, q plus dq, okay, downward meaning minus, upward force is q, okay, and the initial force is upwards, so plus. So, this is the initial force term. Okay. So, the time dependent component we are writing out here. Okay. So, this is the summation of the forces in the vertical y direction. Okay. And if you resolve this thing, that in the differential form, it breaks down to this equation. Okay. After that, we are taking the moment equilibrium about point B, neglecting the rotary inertia effect. Okay. So, what we are doing is that we are taking the moment equilibrium about point B, okay, and we are ignoring the rotary inertia effects. Okay. So, here about point B, okay, we are taking the moment out here. Okay. So, if you are taking the moment, okay, if we are considering the counterclockwise positive, then we will have m plus dm, okay, then we will have minus m. Okay. So, here it is taken clockwise. Okay. So, minus m plus dm, okay, plus m. Okay. So, this two terms comes into picture. Okay. And after that, the effect of the shear times the length. Okay. So, q plus dx times dx. Okay. So, this is causing the moment in this direction. Okay. So, clockwise positive. So, it is causing a positive direction, and the effect of the axial forces. Okay. The effect of the axial forces. Okay. So, here it is having a moment component p times this much. Okay. So, p times this much. Okay. So, moment component, shear component, and the axial applied loading component. Okay. And this reduces down to this equation. Okay. So, we have two equations, one from the transverse vertical forces and one from the bending, okay, taking clockwise as positive, Okay. And what we have done is that we have neglected the higher order terms, and we have neglected the effect of the rotary inertia. Okay. So, these are the two major approximations. Okay. After that, if we take the curvature of the bar related to the bending moment, so basically we are taking the formulation of Euler-Bernoulli beam. Okay. So, we are using the formation of the Euler-Bernoulli beam. So, basically we are using m equals to negative m equals to ei d square y over dx square. Okay. So, we are using the formulation of the Euler-Bernoulli beam. Okay. So, E is the Young's modulus, I is the second moment of area of the bar across the bending neutral axis, okay, and the bar is assumed to be symmetric across the xz plane. Okay. So, there is no twisting in the bar. Okay. So, these are some of the approximations. Okay. We are assuming an Euler-Bernoulli beam, there is no twisting occurring in the bar. we are ignoring the higher order terms, okay, the rotary inertia of the system is being ignored. Okay. So, these are the some of the approximations that is being used to the treatment of the bar. Okay. So, after that what we do is that we have three equations. Okay. One equation from the force balance, one equation from the moment balance, and one from the Euler-Bernoulli beam. Okay. So, after that what we do is that we differentiate the moment equation twice and substitute the expression for shear force and bending moment. Okay. So, then we get the differential equation for the transverse displacement. Okay. So, this is the well known equation. Okay. So, we are already conversant with the equation. Okay. If we ignore this term, we are already conversant with this equation, where this is the inertial term. Okay. This is the stiffness term, and if any axial forces is applied in the vertical direction, then it will show up here. Okay. So, inertial term, stiffness term, and the externally applied forcing term. Okay. So, here the externally applied forcing term is 0, and we are given a force in the axial direction. Okay. Because what we are trying to do is that we are trying to solve for the buckling vibration. Okay. So, this is a fourth order partial differential equation, and it governs the dynamic elastic buckling of the simply supported bar under axial compressive load. Okay. So, simply supported bar, okay, the external load is axial, okay, and it will try to cause the buckling in the bar, okay, and it will mimic the effect such that it will look like a vibration is occurring due to an externally applied lateral load. Okay. This is why it is known as the vibration buckling. Okay. So, after that we use the static buckling formulation and solutions. Okay. So, this was a dynamic equation. Okay. So, it was a time dependent equation. Now, we resolve it. Okay. We simplify it to calculate our static buckling problem. Okay. We simplify this problem, okay, and we ignore the dynamic effects. Okay. So, here basically what we are doing is that we are ignoring the inertial term, okay, and we are left with only the stiffness term and the loading applied in the axial direction. Okay. So, this dynamic equation, we change this back into the static equation. Okay. So, now it becomes the static buckling formulation, okay, and we will try to see the solution for this. Okay. So, how we started the problem? We took a simply supported beam which is uniform. Okay. We put an axial load, okay, that will cause the buckling in the system. Okay. We took out a differential element, okay, and using the force balance, okay, in the y direction and the moment balance, we wrote down the equations. Okay. After that, we assumed that the beam is a Euler-Bernoulli beam. Okay. We use the approximations of the Euler-Bernoulli beam. Okay. We approximated it, we ignored the twisting, we ignored the effect of the rotary inertia, we ignored the effect of the higher order terms, and we got the equation for the dynamic buckling. Okay. Okay. We got the equation for the dynamic buckling, and after that we ignored the inertial terms. Okay. So, we changed the dynamic equation into a static equation. Okay. So, now we will try to see the solution. Okay. So, the static buckling simplification. Okay. So, in the static buckling problem, the inertial term in the governing dynamic equation is neglected. Okay. So, we are neglecting the inertial term. Okay. So, the resulting equation for lateral deflection of the bar under axial compressive load P is given by this equation, okay, or equivalently given by this equation, okay, where we have simplified this equation. Okay. So, for a perfectly straight bar, okay, assuming the bar is perfectly straight, we have the general solution. Okay. So, this is the general solution for a perfectly straight bar. Okay. So, this solution is for a bar with no initial deflection, it is perfectly straight, and the general homogeneous solution is given by this equation. Okay. The deflection has been given by A sin omega x plus B cos omega x plus C x plus D, okay, where omega is square root of beta and A, B, C are constants to be determined from the boundary condition. Okay. So, then we went ahead and put the boundary condition. So, at x equals to 0 and x equals to L, the bar satisfies that the initial deflections are 0. Okay. There is no lateral deflection. Okay. Means at these two ends. Okay. So, remember we have changed the dynamic problem into a static problem. Okay. So, at this two ends, okay, at x equals to 0 and x equals to L, okay, the value of the vertical deflection W at x equals to 0 is 0 and W at x equals to L is 0. Okay. So, these are the two initial conditions. Okay. We have here we have 4 unknowns. Okay. So, we will need 4 boundary conditions. Okay. So, 2 we are taking as the no lateral displacements at the two ends. Okay. The other two conditions are bending moment is 0 at x equals to 0 and bending moment is 0 at x equals to L. Okay. It means that if we put this thing back into our differential equations, okay, if we put into our Euler-Bernoulli beam equations, okay, it means that the second differential, okay, is 0 at both the ends. Okay. For a simply supported case, the bending moment at these two ends, okay, is 0. So, bending moment at x equals to 0 is 0 and the bending moment at x equals to L is also 0. Okay. Then we put this condition into the Bernoulli beam equation, okay, and the second differential, okay, is 0, okay, denoting that the bending moment is 0. Okay. So, using these 4 boundary conditions, what we get is that we get the discrete values of omega n. Okay. And using this equation, okay, we can calculate the corresponding buckling load, okay, or the critical loads for the different omegas. Okay. So, corresponding to different modes of vibration, we will have the buckling load. What does it mean? It means that in order for the system to buckle in this mode, okay, so this is omega equals to first mode. Okay. So, this is the vibration in the first mode. Okay. The buckling shape will correspond to the vibrating mode. Okay. Remember, this was a case of a vibration buckling. Okay. It means that the buckling shape, okay, corresponds to a vibration shape. Okay. So, this is the lowest vibration shape, and in order for the system to buckle, okay, we will need loading equals to this much, where n equals to 1. Okay. So, in order for the system to buckle corresponding to a mode that is resembling the first mode, the loading P1 will be pi square EI over L square. Okay. Subsequently, if the system has to buckle in the second mode, okay, if the system has to buckle in the second mode, P2 equals to 4 pi square EI over L square, and so hence and so forth. Okay. So, for each of the corresponding vibration buckling mode, okay, the load can be calculated. Okay. So, for this load, non-trivial buckle deflection exists. Okay. The magnitude of the deflection W is undetermined, indicating the neutral equilibrium. Okay. So, buckling to occur, okay, in the modes corresponding to the natural vibration of the system. Okay. So, this is the requirement of the axial loading. Okay. So, the effect of the initial shape imperfections and the deflection expansion. Okay. So, we will further look into the effect of the initial imperfection. Okay. So, in real bars, we often have the initial lateral deflection. Okay. So, there is an initial imperfection. Okay. And this initial imperfection can be modeled by a Fourier sine series expression. Okay. So, this is the expression for the initial imperfection. Okay. And this is modeled by a Fourier sine series. Okay. So, this coefficient a n is computed by use of this equation. Okay. So, if we put the initial imperfections in the differential equation, okay, so we are substituting the initial imperfection into the static buckling equation. Okay. So, here we get the corresponding equation. Okay. So, here W is the displacement, okay, measured from the initial deflection, and W naught, okay, determines the imperfections. Okay. So, here in this particular equation, the imperfections are also taken into account. So, what are the solutions? Okay. So, here if you looked into the differential equation, okay, there will be two solutions. Okay. There will be two parts to the solution. One will be the particular solution and one will be the complementary or the general solution. Okay. So, the particular solution, okay, is assumed in this sinusoidal form, and the Fourier coefficient for this solution should satisfy this criteria. Okay. Now, the total sum is the sum of the particular and the homogeneous solution. Okay. Basically, the total solution becomes the solution for the particular as well as the complementary part, okay, or the homogeneous part or general solution part. Okay. We can call it anything. Okay. But basically, it is a part arising, one part is arising from the imperfection condition and the other part is coming from the initial system condition. Okay. And these coefficients are again determined by the boundary conditions. Okay. So, in the first case where we ignored the imperfections, okay, then this was the solution, okay, and the coefficients were there, and we determined the coefficients using the boundary conditions. Okay. So, in this case we introduced the imperfections also. So, the imperfections will contribute to the particular solution, okay, and the initial conditions and the homogeneous solutions will be given by the system again, okay, and again we will have the coefficients which will be determined by the boundary condition. Okay. So, this one will be adding up to the previous solution. Okay. So, the buckling deflection behavior, okay, near the critical load. Okay. So, what happens to the behavior, buckling behavior, when this system approaches the critical load? Okay. As the system approaches near critical load, okay, as the applied load, okay, as the load applied, P applied, okay, it approaches, okay, it becomes close to P critical. Okay. What happens? Okay. As the applied load P approaches the critical load P1, okay, let us say we are talking about the lowest Euler load. Okay. So, here P1 was given by n square pi square EI over L square. Okay. So, this was the deflection caused due to the axial load. Okay. So, this is P and this is P1, okay, pi square EI over L square. Okay. So, as this value of this load is approaching the first Euler critical load. Okay. So, this value is approaching the load, okay, which can cause the buckling in the first mode. Okay. Then Wx is the deflection is been given by this equation, okay, where a coefficient is being introduced, okay, which is a coefficient of the applied load to the critical load. Okay. Here we can see if P approaches P1, okay, the total deflection will theoretically goes to infinity, okay, and this thing is basically indicating a instability in the system. Okay. So, as the applied load is approaching the critical load, it will cause a instability in the system. Okay. So, for the critical load estimation, okay, we can use the midspan deflection. Okay. So, using the midspan deflection, formulation has been proposed by the Southwell. Okay. So, the plotting of delta P versus delta. Okay. So, this is the equation, okay, which can be used for this plot. Okay. So, what it does is that it yields a straight line, okay, whose slope and intercept can be used to estimate the critical buckling load and the imperfection amplitude, okay, where Ai is giving the imperfection amplitude. Okay. Remember here A, okay, is used to determine the coefficient An, okay, it is related to the imperfection that exists in our beam. Okay. So, this imperfection amplitude can be estimated using the Southwell equations. Okay. So, buckling deflection behavior near critical load. Okay. So, this is the P1 line, okay, and this is the deflection line. Okay. This deflection is denoting the deflection at the midspan deflection. Okay. So, as P, okay, as P, this is the plot of the P, as P tries to approach the buckling load. Okay. So, what will happen? Okay. So, we can draw using the equation, we can draw delta P over P over delta. Okay. This is the y axis and this is the x axis. So, if we can draw this, we can estimate the value of the imperfection. Okay. We can estimate the value of A1. Okay. So, the imperfection amplitude we can determine. Okay. So, this is the imperfection amplitude, okay, which we can use to estimate the critical buckling load. For a case, we are taking into account the imperfection that is existing in the system. Okay. So, here, okay. So, instead of using this equation, we can directly calculate the value of An, okay, and from An we can calculate the value of the critical buckling load. Okay. Okay. So, next we see the effect of load eccentricity on buckling. Okay. First we saw the effect of the imperfections on the buckling load. Now we are seeing the effect of the load eccentricity on the buckling load. So, eccentric load is used as an equivalent imperfection. Okay. So, we are using the same thing, same formulations. So, we are modeling the eccentricity as an imperfection. Okay. So, if the axial load is applied with an eccentricity E, okay, the initial deflection due to eccentricity can be modeled similar to an initial displacement. Okay. So, imperfections we were modeling as a deflection. So, similarly, we are modeling the initial deflection due to eccentricity as an case of an initial displacement. Okay. So, the treatment is same, okay, and again we are representing it with a Fourier series. So, the first Fourier series A1 will corresponding to this is eccentricity is given by this formulation. This means that the eccentric loading shifts the Southwell plot intercept to a non-zero positive value. Okay. So, what happens here is that if you look into the Southwell plot, the value of A1 shifts to a non-zero value. Okay. So, the value of A1 will lying somewhere here. Okay. So, due to the imperfection, the value of A1 is negative, okay, and due to the existing eccentricity, okay, the value of this Fourier coefficient is a non-zero value. Okay. So, the modeling of eccentric loading as an equivalent imperfection. Okay. So, if the axial load is applied with an eccentricity E, okay, it means that P is not applied centrally, okay, but it is applied with an eccentricity E. Okay. There is an eccentricity in the application of buckling load P. Okay. The initial deflection due to eccentricity can be modeled similar to an initial displacement. Okay. The first Fourier coefficient of A1 is given by this equation. Okay. So, the Southwell point is shifting towards a non-zero positive value. Okay. It means that the A1 value will be somewhere here, and the first value is given by 4E over pi. Okay. Now, the deflection load relation modifies to this equation. Okay. So, normally it is generally difficult to distinguish between the effect of the initial imperfections and the eccentricity in the experimental data. Okay. So, if we are given an experimental data, it is somewhat difficult to segregate both the effects out. Okay. Okay. So, the empirical observations on the imperfection magnitudes. Okay. So, we have the equivalent eccentricity approximation. So, from the experiments done in the past, okay, we see that the initial imperfection amplitude can be approximated by an equivalent eccentricity. Okay. So, we are modeling the effect of the initial imperfections by an equivalent eccentricity. Okay. So, where RC is the core radius of the cross sections. Okay. So, eccentricity due to the imperfections, okay, or the imperfections model as its eccentricity is given by this equation. Okay. Imperfections also depends upon the column length. Okay. So, if we looked into the data, okay, the imperfection amplitude tend to increase roughly in proportion to the column length. Okay. So, the amount of imperfection, okay, will grow as the length of the column grows. So, the approximate range for imperfection amplitude is normalized by a radius of gyration, which is given by this equations. Okay. So, here we are, what we did was we took a perfect case. Okay. We evaluated the value of the critical buckling load. Okay. After that, what we did was we evaluated the expression for initial imperfections. Okay. Then we also evaluated for eccentricity in the loading. Okay. And then we are modeling the effect of the eccentricity as an equivalent imperfection. Okay. and from the historical data we can have an estimate of how much is the magnitude. Okay. So, this is how we are trying to deal with the calculation of the buckling load in the vibration type of buckling. So, we saw a case of a static buckling, okay. We saw a case of the static buckling, okay, where the buckling shape corresponds to the mode shifts under the normal vibrations. So, we will stop here and I will request you to do the exercises. Thank you.